Okay. So today we are going to start talking about missing data. Before I get into that, were there any questions that weren't asked on Piazza about the assignment? Okay. So I didn't put this on the slides, but I just, if we think, before we start thinking about missing data, we can think about the case where we have data that are observed, but we know that our measurements of the data on the predictor X have measurement error in them. So measurement error is one of these odd things in the social sciences where we've pretty much decided as a community to just let it slide for like every study that's published in a social science journal. So there's no one in the social sciences who makes the argument that our variables are generally measured pretty well. So everyone understands that a lot of the key variables that you measure in the social sciences are measured with considerable amount of error. And it even would be a stretch to say that, you know, the measurement error in these things is random. It'd be quite uncontroversial more in particular cases to say, well, this measurement error is just systematically wrong. But there's no one out there, you know, saying that these things are measured well. At the same time, there's no one out there who's making the argument, at least in general, that measurement error isn't a problem. So if the measurement error is only on the outcome variable in like a linear regression, then it just makes sigma greater. It makes the uncertainty in the estimates of the coefficients greater. It doesn't cause any bias. But that's only in the case of a linear model and measurement error only on the outcome variable. If you have random measurement error on exactly one predictor, then we know it's the case that random measurement error on that predictor will make the estimated coefficient be closer to 0 than it is if you were to use the true data. And so that is thought to be not that bad because, you know, if you underestimate something, you estimate it closer to 0. But you're still able to sort of reject the null hypothesis that it is exactly 0, then you've more or less accomplished what you set out to do. But in the case, well, suppose we have measurement error on a control variable, but we're actually interested in the coefficient on another variable. Then all bets are off as to what the effect would be on the coefficient of interest. What if you have measurement error on multiple predictors? Then we can't say in general what the direction of the bias is, but we know that the estimates that you would get out of estimating such a linear model are not unbiased. They're not consistent. They don't have any of the properties that were originally used to justify these estimators. So everyone recognizes measurement error is a problem. No one says, or measurement error is prevalent. No one says that, you know, measurement error is not that big a deal for statistics or quantitative estimation, but, you know, you don't get papers rejected from journals just because your variables are measured with a considerable amount of error, because there wouldn't be journals. If that was the stint, there'd be, you know, nothing to publish. And, you know, reviewers are often sort of drawn from a pretty small pool. You know, why is it that one person should have their paper rejected because they were using variables that were measured with a considerable amount of error, when, you know, lots of other people in that same issue of the journal are publishing papers that are also contaminated by measurement error. And so the editor of a journal, in most cases in the social sciences, is just going to be like, you know, what are you going to do? So what you could do is estimate the model with Bayesian techniques, in which case it's not really that much harder than what you would do if you happen to measure your variables accurately. All you need to do is posit the existence, which is to say declare unknown parameter vector that contains the true value of the you know, thing that's measured with error, and then relate that true variable in some model that you're interested in. And so I've done that here. I didn't put this in the slides, and this computer doesn't have RStudio on it, so I had to just type it in a web browser, but it was less than 20 lines. So you know right away this can't be that onerous. You declare what n is. You declare your observed x, but in this case we're thinking about x as being contaminated with an unknown amount of error, and we're going to estimate what the true x is, and we're going to estimate what the error standard deviation of the measurement error is. You have some outcome variable y. In the parameters block, you have an intercept, you have a coefficient, and you have a standard deviation for the errors in y. We're just going to be doing a linear regression model here. So this is pretty much the same as the linear regression code that we wrote before. The difference is that we have two additional parameters, x underscore true and sigma x. X underscore true is a vector of the same length as x observed. This is going to represent the true values of the thing that x is ostensibly trying to measure. And in this case, to keep it simpler, we're just thinking about there being some random measurement error. You could do more complicated things if you thought there would be systematic measurement error. And then in the model block, the first thing we say is that our observed measurements of x have a normal, you could call it likelihood, conditional on the unknown true value of x. So we're thinking of, you know, nature has some true value of x. We measure it with unknown random error, but it's sort of on average equal to x true. And then we have sigma underscore x as the standard deviation of that part of the process. Then on the next slide, we have what you might call the true likelihood of y. So y has a normal likelihood as well. The conditional mean of y is the intercept plus the coefficient multiplied by x true rather than x ops. And so this is, you know, corresponds to the theoretical relationship that you think should exist in the data. The outcomes, insofar as they're a function of x, are usually thought of as being a function of the actual x rather than the measurement of x that's obtained by the researcher subsequently. Now, in some situations, it may be that your units of observation also misperceive or mismeasure x. And so the data generating process actually corresponds to what the people in your study perceive x to be rather than what x actually is. And so you could do a model for that. But in the usual case, we're thinking of the outcome as being generated by the true x. And so we're going to use x underscore true as our predictor rather than x underscore obs, which has the random error in it. Then, and there's standard deviation of the errors in y, sigma y. Then we just need to put priors on the remaining parameters, alpha, beta, sigma y, and sigma x. Now, this model was very easy to write down, and it would work way better than what people typically would do, which just do a regression of y on x obs. But in a model like this, where you have, you know, n plus 4 parameters and only n observations to estimate it with, putting prior information, good prior information on those other parameters becomes more important than in some of the models that we started with RStanArm and things like that, where, you know, there weren't that many parameters. There was a lot of information in the data on them, and you could get away with, like, you know, weakly informative, even sort of preposterously weak priors on the parameters. If you have a model like this, it's going to be more important, unless, you know, xobs only has like a little bit of measurement error in it. It's going to be more important that you put in your actual beliefs, particularly about sigma x. So this is the standard deviation of the errors in the data generating process for which your observed x gets generated. So it's going to be important in a model like this to have some sort of informed belief as to how bad the measurement error is. And so, you know, there's a variety of ways you could come up with that. Maybe you have 2 measures of x, and so you can incorporate those and use like the same standard deviation for both of those anyway to get a little bit more information on, you know, this part of the model relating your measurements to the actual thing that you were trying to measure, and failing to some extent. It's also important to have priors, at least weakly informative priors on alpha, beta, and sigma y. But particularly in a model like this, it's important to have a good prior information on the degree of measurement error. But other than that, it's pretty simple. It's not really harder than any of the models that we've been talking about before. And, you know, this is really one of the, you know, main advantages of the Bayesian approach, and that you can express your beliefs about how badly x is measured as part of the model, and you can write the model where y is a function of the true x rather than the observed x. You can't, you know, do something like this in, you know, some frequentist estimator because you have more unknowns than you have observations. And all the conditions under which a frequentist estimator are going to have some good properties on average over repeated gatherings of the data, that's going to require the number of parameters be fixed and small relative to the number of data points. And so in a model like this, you cannot consistently estimate alpha and beta and the sigma y and sigma x with like these squares, or maximum likelihood, because you have too many parameters. But from a Bayesian perspective, just counting up the number of parameters is kind of a red herring. Sure, we have n plus 4 parameters here, but we have prior information about those parameters, and particularly for x true, we have, you know, the prior information that our observed value is, you know, on average equal to the true value, and we have some prior information on how much variance there is to that relationship. So it's fine to have n plus 4 unknowns and only n data points, if you're able to express, your beliefs, some information about this through the priors and through the choices that you make with the likelihood and things like that. So this is not a particularly complicated Bayesian model, and at least in the assumptions that I made here, that you just have random measurement error, one predictor, whatever, it's a perfectly good solution to a problem that there really isn't a frequentist solution to. And it's a problem that is extraordinarily prevalent in the social sciences. It's just a little bit more complicated because you usually have several X's, and several of them may have measurement errors, so you'd have to sort of do this. For each of those, it's possible the measurement error could be correlated. That may be kind of unlikely, but it depends on how the data were collected and things like that. So questions about something like this?
The vector for the x true, the length should be the ZF vector for the x of the.
Yeah. So we're assuming that everybody's x is measured with some error. But, you could come up with situations in which, maybe you think you have pretty good, almost correct x measurements on like some people, but really bad estimates of x on other people. You could write down the model where you only had measurement error for, some people, and that was added on for those people, but, other people you think you have it measured pretty well. So you don't have to have them be the same length, but you do have to incorporate them into a reasonable model of the data generating process as a whole, inclusive of the process by which you as the researcher come to be in possession of, this or that measurement of X. So point of this is that dealing with measurement error in the variables is, not that difficult. It ought to be automatic. It's not particularly more difficult than the sorts of things that we've been talking about before if you can write down a Stan model or a model in the Stan language.
If there is like a bias, there is like saying, let's say the value, true value is near 0, the error is like 5 plus or minus some small number, like randomly around 5.
Uh-huh.
And like that means it's absorbed into the slope of 32%.
Yeah, so you get a bias estimate of the intercept, but your estimate of the slope might not be that bad. But if you had reason to think, okay, I'm not randomly mismeasuring X, I'm systematically underestimating X, then you would want to have some coefficient on the relationship between X true and X that's like constrained to be between 0 and 1. So all of that is part of your beliefs about the data generating process. And, if you can write down what your beliefs are, you can update your beliefs conditional on the data that you observe. You can update your beliefs about everything jointly, alpha, beta, sigma. If you're interested in the true values, you get posterior distributions of all those. So you get it all. Questions?
Is this mostly for experimental data? Or because in real life data it's harder to we know less about the world.
Yeah.
Does this case mostly come up? This kind of come up?
I mean, the logic of it is sort of indifferent as to whether you've done an experiment with poorly measured things or, observational study with poorly measured things. At least in the experimental case, you shouldn't have any mismeasurement on the treatment variable because you assign that. Or you assign, something that randomizes who gets put in treatment and who gets control. You can certainly have measurement error on the predictors. You can have measurement error on the outcome. But all that is true in observational studies as well. At the point at which you're writing down the stand model, it doesn't really matter if it was an experiment or not. I mean, that's an important thing to think about if you want to interpret your estimates as causal effects. It's an important thing to think about, you know, if you do an experiment on some non-representative group, making inferences to the population as a whole, you know, that's important to think about. But just in terms of writing down the stand code, the logic of that, it doesn't matter, really. Yes?
How do we know, like let's say we thought there was measurement error, like we knew that only a third of our data had been actually validated. Is there a way to use this to say, turns out that didn't matter, or turns out 2/3 of this data is in fact screwed?
Well, so typically you would know like whether 1/3 of your data is validated. So you estimate measurement error on the rest of it. You could find that sigma x is very close to 0. In which case the posterior distribution, the posterior means at least of x true is probably going to be very similar to x obs. So yes, you could, not knowing it in advance, but update your beliefs as to how well you measured that x. But it tends to be worse than you think rather than better. Okay, so missing data is, you know, kind of an extension of mismeasured data, or maybe mismeasured data is a special case of missing data. In the example we talked about before, the true x was missing, but we knew it was related to the observed x. We believed it was related to the observed x through a simple process. What we're going to be talking about today is more, I guess, like conventional missing data, where like you ask somebody a survey question and they decide not to tell you. So you really don't have any measurement for that person, although you do have measurements, maybe with error, maybe not, for the people who decide to answer the questions. So, you know, the first thing, just like there's no frequentist estimator really when x is measured with unknown amount of error, there really is no frequentist perspective on missing data, even though you'll encounter frequentists talking about missing data. If you just go back to the definition of probability from a frequentist perspective, you can immediately recognize that the frequentist, you know, paradigm of probability is not general enough to handle the missingness. So remember, probability of event A occurring is defined from the frequentist perspective as the proportion of times that A occurs as the number of independent trials goes to infinity. So let's say A is just has a binary sample space 1 or 0. So we can write this as the limit as the number of observations goes to infinity. In the numerator, the number of times that A occurs, and in the denominator, the sum of the number of times that A occurs and the number of times that A doesn't occur. That's equal to n. So, okay, that's like kind of a weird way to define probability, but it immediately doesn't work if in that sort of imaginary thing where you imagine this process repeating, you know, over and over and over again, if there's some non-zero proportion of the trials where we don't know whether the outcome is A equals 1 or A equals 0. In that case, we're never going to be able to get a unique number, a unique limit for what the probability of A is. We could put a bound on it. So you could assume like all the missing trials are A equals 0. And then you get like a lower bound for the probability of A. And you can assume all the missing trials have A equals 1. And you would get an upper bound for what the probability of A is, but you're never going to, if a non-zero proportion of those are missing, you're never going to be able to take that limit and come up with a unique value for the probability of A. You could assume that the proportion of times that A occurs in the unobserved data is the same as the proportion of times that it occurs in the observed data. But one, you're basically expressing your beliefs at that point, rather than saying like, I'm just going to look at the data. And your beliefs may be wrong. So you can assume the missingness aspect of it is independent of the value, and then do that. But that already seems like contrary to sort of the frequentist view on probability. The only thing that you can sort of rigorously do, maybe from a frequentist perspective, is to consider the missing values as unknowns. You don't know what the true value is, and you could try to write the likelihood function integrating out those unknown values of whatever it is, and come up with a likelihood function that only involves the observed data that you see. And that's about the only thing you can do from a frequentist perspective that's rigorous, but you typically almost always are not going to be able to get that integral in an analytical form. So you're going to be reduced to doing some sort of numerical approximation to the integral. And that's the same problem that Bayesians were stuck on for like 100 years. Is, they couldn't do the integral in the denominator of Bayes' rule, had to come up with like MCMC sampling schemes to, get around that problem. And so in order to even evaluate the likelihood, you would probably have to be doing like Monte Carlo estimates of that likelihood of the observed data. So there's really no good alternative for how to approach missing data from a frequentist perspective if you're not going to introduce your beliefs about what the missing values are. And it comes directly from the definition of probability. When they were coming up with this, that was well before anyone started really worrying about missing data. Of course, Fisher and Neyman and those people, they had missing data back in the 1920s and the 1930s. But they didn't really, think about that. And so they didn't build into the, the definitions that they were using to, build up probability and statistics as a discipline to be, general enough to incorporate something like this. Also, it has to be emphasized that there was no such thing as social science back then. So they weren't thinking first and foremost about applying this statistics stuff to social science questions. That came later. And in the social science realm, you can't really avoid the fact that you're going to have missing data a lot of the time. So there's not much you can do from a frequentist perspective because they didn't define probability in a general enough way. What some people are tempted to do, which is just wrong, is to treat the missing values as unknowns and maximize the likelihood over like alpha and beta and all the unknown missing values. And what those people are forgetting is that the justification for maximum likelihood, it being a consistent estimator, it being asymptotically normal, etc., all relies on the assumption that the number of unknowns remains fixed as the number of observations goes to infinity. That's a condition for it to yield consistent estimation and things like that. If you have, missingness on the income variable, if you imagine yourself getting more and more observations, you're going to get more and more missingness on your income variable. And so treating the unknown values of income as parameters and choosing the values of it to maximize the likelihood, numerically speaking, it can be done. It's a big optimization problem. But the resulting estimates don't even have the properties of maximum likelihood estimates. They're not consistent. They're not asymptotically normal. They're not approximately equal to Bayesian posterior mode. None of that. So you just have this number that you can call an estimate, but it has no known good properties. And, Neyman and a co-author of his, Betty Scott, was sort of the first people in a social science journal to call this thing incidental parameters problem, which is basically the situation in which the number of parameters grows at the same rate as the sample grows, and all the bad things that happen to the estimators in terms of them being inconsistent and whatnot. So Neyman and Scott, knew about this in the 1940s, but they didn't really have a general solution to a problem like this. And this, as we talked about, both missing data and data measured with error are the rule rather than the exception in the social sciences. And so if we took missing data and mismeasured data seriously, there just really wouldn't be that much of a role for using frequentist estimators in the social sciences. But there was decades and decades in which that was about the only thing that you could do. Do some frequentist estimator and just kind of pretend that there's no missing data, pretend that there's no measurement error on the predictors, and you get numbers. But those numbers don't have the properties that as estimators, or those estimators don't have the properties that Fisher and those guys proved would hold for if your all data was fully observed, you're measuring it correctly, you have a lot of it, etc.
MFE and NME would be the same bucket there, right? Problems.
Huh.
MFE would have maximum.
Yes.
Problems, right?
Yeah. Right. So this I think is one of the simplest sufficient arguments as to why you should learn the Bayesian approach if you're doing social science problems or even other problems in other fields that also presumably are going to have missingness. They're going to have measurement error. You have to introduce your beliefs as to what the true values are. But once you do that, then it's not really harder than any of the rest of the stuff that you had to learn when you were doing Bayesian stuff. So it might be a little weird to make a simple sufficient argument as to why you should learn Bayesian statistics when there's only like 2 weeks left in the semester. Maybe I should have pointed this out at the second week of the semester. But I pointed out a bunch of stuff back at the beginning of the semester as to why this is an important thing. And it's not as if there's a whole lot of arguments against the sort of things that I have on this slide. It is just doing the Bayesian approach was technologically impossible for a long time, technologically difficult and not very reliable for like 20 years. And now it's sort of technologically possible to do it, pretty well, pretty easily. All right. So the Bayesian perspective on missing data is that the true values of the missing data are unknowns, and we have beliefs about those unknowns, and we're going to describe our beliefs about those unknowns with probability distributions. We're going to condition on the data that we observe. We're going to update our beliefs about all the unknowns collectively, including the true values of missing data, including the parameters, and we're going to get draws from the posterior distribution of everything. So it's not a fundamentally different perspective than how we think about theta or beta or sigma or whatever, even in the case where all the data is like perfectly measured and fully observed. We kind of already dealt with missing data in one form when we talked about the ordered probit models that have this utility y star, which we integrated out. So that was one of the rare cases in which you can integrate the unknowns out of the likelihood. But you know, that was, I guess you can think of it as missing data. We're never going to observe utility. We're just going to observe the choices people make about this. But you know, dealing with the more classical missing data where people refuse to answer questions is a little bit tedious, but it's not fundamentally difficult from the way in which we think about the distribution of any unknown, whether it's future data, parameter values, anything like that. So to help us do that, let's let the capital R boldface be a matrix, or when it gets represented in Stan, it could be an n by k array. And the elements of R are binary. And so they're equal to 1 if the observation for the kth variable on the ith person is observed. And R is equal to 0 if the kth variable on the ith person is missing. Like they refuse to answer the question. So that R matrix is basically always going to be fully observed. You should know whether your data are observed or missing. There's very rare cases in which you would have uncertainty about that. Now, you might not know how much measurement error there is in the observed values, but you should know if the data are observed or missing. So we'll just consider R to be, you know, complete, consisting of 1 and 0s. So then let's let X superscript M stand for like the true values of the missing data, and X superscript O to underscore like the collection of all the values of observed data on these K variables. And one thing that I think helps, but is maybe a little bit contrary to the way people usually think about this, we're thinking about these, you know, structures and equations and stuff as existing before the data are collected. So we're thinking about this thing like we know that there's going to be missingness on income and race and, you know, a bunch of other variables, but we haven't tried to collect the data yet. So we don't know whose income is going to be missing and whose is going to be observed, or, you know, the other education and other variables like that. So we're thinking about specification of this data generating process before we have realizations of the data. So we know that like some of X is going to be observed. We know that some of X is going to be missing, but we don't know which is which yet. So at this point, you know, all the X's are sort of to be determined. And the same thing with R. You know, we know it's going to be n by k. We know it's going to have 0s and 1s, but we don't know which cells are 0, and we don't know which are 1 yet. So there's going to be 2 types of parameters generically. Theta, that's a vector of parameters for the so-called substantive model, the model that you would estimate if everything was fully observed. And we have another parameter vector, phi, which stands for the parameters of the missingness model. So in general, we're going to have to incorporate a model for R into our Stan program, or, you know, whatever Bayesian thing we're using. And so that missingness observed part of the model, the not substantive one, is going to be governed by some parameters phi. And so then we can write down Bayes' theorem, again, before we've gone out and tried to collect the data, as a posterior PDF for theta, for phi, and for all the missing values, conditional on all the observed values of x and the matrix R. And so that, if we ignore the denominator, is equal to a prior on theta and phi. Usually, we're going to assume theta and phi are independent of each other a priori. So we could write f of theta and phi using the general multiplication rule in the case of independence as f theta times f phi. And so we could have independent priors on those two things. But that is not super essential. And then we have what's known as the complete data likelihood. So the likelihood for x and xm and xo joined together, conditional, and r, so r is also observed, conditional on theta and phi. So even though xm is not observed, we're usually going to assume it's generated with the same data generating process as the observed values. We just don't know what the missing values are. So then we can write this complete data likelihood like this. The likelihood for xm and xo together, conditional on theta, multiplied by the likelihood for R, conditional on phi and the union of xm and xo. So the general multiplication rule implies that this line here is equal in distribution to the line above it. So we've written the likelihood for xm, xo, and R as a likelihood for xm and xo conditional on theta, but not R, and then multiplied by a likelihood piece for R conditional on phi and the missing and observed values for x. And so this, in general, allows for R, which is 1 or 0, to be a function of the x's, the true values of x, and in the case that it's missing, and the observed values of x in the case that it is observed. And so this is typically important for a lot of things in social science where, if the x is like unfavorable, there's a higher probability that it's going to be missing, not reported in the data. This is both, a well understood pattern for individuals. They're less likely to report data that reflects, poorly on them in surveys or other things that they feel are like private information. But it also applies to governments. With government data, they're less likely to release it if it reflects poorly on the government or whoever is currently in power in the government. And so we want to at least think about the possibility that R could be a function of X. And then, so here we see theta is pertaining to the substantive model, like how X is generated, and phi pertains to how R is generated, and they don't cross over. Or there's another way we could write this, which is also equivalent to the first two, prior on theta and phi, a likelihood for R given phi and the observed data, and then a likelihood for the missing data conditional on R and theta and the observed data. That's just different ways of writing out the general multiplication rule. They're all equal to the first line here, which is sort of prior on the unknown parameters, and then complete data likelihood. Yes? We don't know. So we don't know how many, in advance, we don't know how many X's are going to be observed and how many are missing. But we're sort of thinking that there could be at least one in each bucket. R is n by k, and let's say that there's k x variables we're observing, trying to observe.
So that's the relation between x m and xo and r. R is the representation of this.
R is basically just indicating whether the thing is missing or observed. So you can imagine, okay, I have a big X matrix, not necessarily that big, but K columns. Some of those are going to be NA. And then you have a R matrix that's the same size. And for every cell of X that's NA, R is 0. And for every cell of X that's not NA, which is to say you observed it, R is 1. And then XO would be, you can think of this as like a long vector. If you just take all the non-NAs out of X and make it a long vector. And then XM is the true values of the things where, everywhere you have observed an NA in the thing. So you have these two long vectors that if you put them together according to R, you would have the true X matrix. But you don't know what that is, but you have beliefs about it that you can update.
Right, so, but in here, like R is the only thing that's known. XO and XM are not known yet.
Well, XO will be known once you collect the data.
Yeah, but for the purposes of this much.
Before you collect the data, yeah, we're just thinking of all these as random variables that you haven't collected yet.
Only R is to observe in this formula right here, where it's treated.
Yes, R, you will never have missingness in R. Once you collect the data, you'll know what XO is. You won't know what XM is, and you need beliefs to be updated about those. Or if you get extremely strong assumptions, to integrate XM out of this and just make inferences about theta and phi and that. So the most common way of thinking about the posterior distribution, this is just what I wrote on the previous page again. We have priors on theta and phi. That's kind of what we've been doing before. We have this complete data likelihood, which is going to be the joining together the true values that are missing with the observed values of X. That depends on theta. And then we're going to have a so-called missingness model, missing this piece to the likelihood for R, conditional on phi, and both the true and the observed values of X. And so that is the other piece that's pretty much necessary for Bayes' rule to go through. So we're going to have to think of a substantive model, which is sort of represented by the complete data likelihood, and a missingness model, who's observed, who's not observed, and think about why that may be. So the missing data literature is plagued by some ridiculous acronyms that you just have to learn. One is missing at random, or MAR. And we say a data generating process is missing at random if two things are satisfied. One, the prior on theta and phi are independent of each other, in which case we can just write them as a product of two densities. And the missingness model for R conditional on phi and XM and XO simplifies to a model for R given phi and XO only. So why might that be the case? Let's say you have one variable in X that's fully observed, and you have another variable in X that's like partly observed, partly missing. If the first variable explains all there is to explain about when the second variable is observed and the second variable is missing, then R doesn't depend on the second variable. It just depends on the first variable, which I'm supposing here is fully observed. So if you can write down your missingness model, and in fact, it doesn't involve the true values of the observations that are missing, then, okay, this simplification happens. assuming prior independence is usually not that big a deal. And so if both of those hold, then this data generating process is said to be missing at random. An even stronger condition is called missing completely at random, or MCAR, if the stronger assumption that the missingness for R, it doesn't even depend on the observed values of X. It just depends on phi. So phi could be like a weighted coin flip. You know, maybe it's like 0.8 or something like that. It's some unknown parameter, you could estimate it. And just, you know, whether an observation is observed or missing is just the result of a flip of these coins. Doesn't have anything to do with the true values of X, whether they're observed or whether they're missing. So missing completely at random is a stronger assumption than missing at random. Missing completely at random is abbreviated MCAR, but people usually forget what the C stands for, and they think MCAR means missing conditionally at random. But missing conditionally at random is actually a better description for MAR, missing at random. So missing at random basically says conditional on the observed X. The missing X doesn't matter for predicting R. But that's called missing at random, not missing conditionally at random. If the data generating process is missing at random, then we can, basically it comes out to the case that these two parts of the model, for the substantive part and the missingness part, are conditionally independent of each other. So we could do them in like separate stand programs. But if we could do them in separate stand programs and we didn't really care about the missingness model, then we could just not do the missingness model. We could just do the substantive model. Now that doesn't mean when data generating process is missing at random that you can just analyze the observed data. Like throw away any people where you have missingness, because the substantive model you still have to consider XM to be unknown. This is pretty much what we were doing when I started off and we had measurement error. We still had to do like X true, but we didn't have to model any R or anything like that. So if the data generating process is missing at random, the two parts of the model are independent of each other. You could update your beliefs about theta independently of your beliefs about phi. And if you actually don't care about phi, then you don't need to update your beliefs about phi at all. If the data generating process is missing completely at random, then you could just do a model with theta and XO. And so that's what making these really strong assumptions buys you. But in general, the data generating process is going to be neither missing at random nor missing completely at random, in which case the data generating process is said to be missing not at random or not missing at random. But missing not at random and not missing at random are the same concept. So you'll hear people refer to MNAR, missing not at random, and NMAR, not missing at random, and those two are the same thing. Questions? In general, things are missing not at random, in which case, in order for you to apply Bayes' rule, you're going to need a substantive model for like the X's and the Y's and a missingness model for R as part of the same stand program. Question? Okay. So multiple imputation is something that you may have heard of. Actually teach an entire class in the QMSS on missing data that's sort of heavily focused on multiple imputation. But you know, the reason why I can teach a whole semester class on missing data, and then in the Bayesian class we can pretty much just spend like 1 week on it, is because the missing data class is always like dancing around the idea of, well, you should just write down a posterior distribution and draw from it with standard. So like, if I was allowed to really say that in the missing data class, then there wouldn't need to be like a whole semester on it. It could just be a week, but you get like 4 credits. So we have to come up with like 14 other weeks and not really mention the whole Bayesian idea. But, you know, if you did, you know, to teach the Bayesian thing, then the missing data class would actually be the same as the Bayesian class. But multiple imputation is fundamentally a Bayesian idea that frequentists have adopted. So instead of modeling these two things together, they will assume the data generating process is missing at random, often with not even bother to give a justification for that, but to assume the data generating process is missing at random, and then proceed in 2 stages. At the first stage, we'll draw from the posterior distribution of xm. And then once we have xm, we'll combine it with the observed data that we have, and now we have a bunch of completed data sets. Now in these completed data sets, the observed values for the x's and the y's and whatever, they're the same in each data set. We observed them. But for the values that were originally missing, we have draws from the posterior distribution of xm that we're sticking into a data set. So we get these multiple data sets that differ only randomly in the values in the cells of that data set that were originally missing. And then we're going to take those completed data sets, completed by the original observed data and draws from the posterior distribution of xm when necessary, fused together, and we do that a bunch of times. So we have multiple completed data sets, and then apply some estimator, usually a frequentist estimator, on each of those completed data sets. So now we get a bunch of maximum likelihood estimates or something like that. And then we're going to average those maximum likelihood estimates across the completed data sets to get one estimate of the thing that we're doing. So multiple imputation is one, assuming missing at random, so you don't have to model R. And then instead of drawing from the joint distribution of xm and theta, trying to first draw from the posterior distribution of xm, use those completed data sets to then get maximum likelihood estimates of theta, several of them, because you have several completed data sets, averaging those maximum likelihood estimates together to get a single estimate of theta. But it's fundamentally a Bayesian idea because you're drawing from the posterior distribution of xm. It's just you're drawing from the posterior distribution of xm and then evaluating the expectation of some g function, but the g function happens to be a frequentist estimator. So you're getting maximum likelihood estimates averaged over the posterior distribution of xm. So specifically, you draw from an approximation to the posterior distribution of xm. You do that capital M times to form capital M completed data sets. These posterior distributions, they tend to try to make weak assumptions about the data, except that the data is missing at random. And then, so you have M completed data sets, you execute your frequentist estimator on the M completed data sets, and then you combine the M estimates according to the so-called Rubin rules. So these rules were formulated by Don Rubin, who is one of the most prominent Bayesians and has even harsher things to say about frequentists than I do. But somehow the frequentists haven't caught on to the fact that if you're using Rubin's rules, this is a Bayesian procedure rather than a frequentist procedure. So you have a point estimate, which is the average of the M point estimates, and you can estimate the variance covariance matrix of the estimator using some formulas that involve an inflation factor of 1 plus 1 over M. So you want M, the number of completed data sets, to be large, so you're not inflating your variance up that much. And it turns out that under the missing at random assumption, this procedure is actually good in the frequentist sense. That if we were to do this over and over and over again, like our 95% of the time, the true thing would be caught within the confidence intervals and things like that. But that just is underscoring the point that Bayesian procedures have perfectly good frequentist properties. If you take a Bayesian estimator and you do that like over and over and over again with different data sets drawn from the same population, you'll get a distribution, and 95% intervals are going to capture the true parameter 95% of the time. The reason why that's true is the Bayesian estimator is justified on each data set. It's conditional just on that data. And so if you do that over a bunch of data sets, you get a distribution of point estimates, but that distribution of point estimates has the same good properties as the distribution of frequentist point estimates. It's just Bayesians are considerably more reluctant to imagine, what would happen if I did the same research project over and over and over again, because, no one actually does that. But this procedure, it's essentially Bayesian. It is a proper imputation algorithm if it yields consistent point estimates as the number of observations goes to infinity, and 95% confidence intervals have catch the true parameter 95% of the time when you do this. So you can derive something like that, and multiple imputation algorithms are built into a lot of software, including R and Stata. So does anybody have any questions about the basic idea of multiple imputation? That's like a month in the other class.
The second thing is like the MLE or map thing, the estimator.
It's not even map. It's usually maximum likelihood. But you could do a Bayesian estimator in step 2 as well. Yes?
What happens if you're pretty sure that it is? Can you still do this?
You'd be wrong. So it's a proper imputation algorithm under the missing at random assumption. It isn't consistent if the data are missing not at random or not missing at random, which again are the same thing. And you don't need to do it if the data are missing completely at random. But that's just a really strong assumption to make. So one of the popular ways of doing imputation is to assume that X, like the data generating process for X, is multivariate normal, whether the thing is observed or whether it's missing. Like the true data generating process for X can be described by a multivariate normal distribution with unknown mean vector and unknown variance covariance matrix, in which case the Amelia package in R, Stata, SAS, they all have algorithms for multivariate normal imputation that are basically just approximations, not very good approximations in some case, to the following pretty simple STAM program, which has to go on 2 slides, but it's not particularly complicated. So what we have in the data block are N, the number of observations, K, the number of variables. We have a 2-dimensional array called R that's N by K, whose lower bound is 0 and whose upper bound is 1. And that tells us which observations in the sort of X matrix that we have in R are observed, which are missing. And then we have a long vector of observed values on X. So the number of observed values on X is the sum of the R array. And we're just going to string those out in a long vector, pass them in from R. They need to be, the way this is formulated here, in row major order. So let's say X11 is observed, X12 is observed. You're looking at this the other way. X11 is observed. The thing to the right of it is observed. The third variable for the first person is missing. So XO would have like the first, the 1-1 thing, then the 1-2 thing, skip the 1-3 thing. Maybe the fourth variable for the first person is observed. That would be the third element of XO. In other words, it goes from left to right, top to bottom, which is how you like read in English. But R by default stores things from top to bottom, left to right. So it's really like the transpose of X, if you're thinking about how this is stored in R. But we'll get practice with this. So we have N, we have K, we have R, which is N by K, and we have a long vector for all the elements of X which are actually observed. The number of that is equal to the number of ones in R. So far, so good? Then in the parameters block, we have the complementary thing, X underscore M. And this is going to be equal in length to N times K, which is as big as it could be, minus the sum of R. So this is equal to the sum of the number of zeros in R. So XO and XM are like complements. Together they have length N times K. Then we have parameters that go into this multivariate normal, a mean vector mu, and a Cholesky factor of a covariance matrix L. And we're going to estimate mu, L, and XM all at the same time. Questions so far? L is the Cholesky factor of the covariance matrix in the multivariate normal distribution. Yes? Because it's zeros and ones rather than real numbers, I declare it as an array. You actually could be a matrix that has like 0.000 and 1.000. That's fine. Takes up a little bit more storage to store them as real rather than integers. We're not multiplying R by anything, so I tend to only use matrices when I'm doing like matrix algebra with them. Okay, the model block looks like this. So we're going to have a thing that kind of sounds like a matrix but actually isn't a matrix. So we're going to have an array. This array is of length n. The name of the array is X underscore C for completed X. Each element of this array is a row vector of length K. So if we're thinking about this in R, this is like a list with n elements. Each of the elements of that list is a row vector of length K, and the thing is named X sub C for X completed. We're going to create observed mark and missing this mark. We're going to initialize those to 1. We're going to loop over the observations. We're going to loop over the variables. And inside the loop, we're just going to stitch together XC, either taking from XO if the thing is observed, or taking from XM if the thing is originally missing. So if RIK is 1, then we're going to extract the next element out of XO and stick it into XC. And when we do that, we're going to bump up observed mark by 1. If RIK is 0, then we're going to extract the next element out of XM, stick that into XC. So XC is the completion of XM and XO. We also bump up the missingness mark when we do that. So we loop over all the observations, we loop over all the variables, we fill in XC. Some of its elements are known data, others of its elements are unknown parameters that come from XM. Doesn't really matter. At the end of both loops, we just have a complete data likelihood statement. Multivariate normal using Cholesky underscore LPDF for X sub C, conditional on mu and L. Then we have priors on mu and L, and that's the end of our STAM program. So what, all these multivariate normal imputation algorithms are trying to do is draw from the posterior distribution of XM. And you could do that with like the same assumptions they're making using a STAM program that's not too complicated. All you have to do is join together XM and XO in the appropriate fashion to make XC, complete dated likelihood on XC, priors on mu and L, and then STAM will run. But if you can do this, you could immediately or almost immediately extend your STAM program to do stuff that's not implemented in Stata or Amelia or whatever. So what if you didn't want to use the multivariate normal distribution? What if you wanted to use multivariate student T so that the variables had like longer tails, which is not uncommon in social science? Then we would just change the multivariate normal to multivariate student. What if we wanted to estimate a distribution where the variables could be skewed? We could use, some other distribution. What if we wanted to not assume that the data were missing at random, and we wanted to add on a part of the model that modeled R? And so allowing the data to be missing not at random or not missing at random, which are the same thing. We could easily do that in a STAM program. So all of those things, they're not, programmed into these multivariate normal imputation algorithms, because then it would be really hard for like Stata or whatever to estimate mu and L if you didn't assume it was multivariate normal. You assumed it was like some other distribution. A lot of these approximation algorithms use tricks that only work for the multivariate normal. But in STAN, it doesn't really matter that much if it's multivariate normal, if it's multivariate something else. You assume, whatever distribution you want in the likelihood, and then you can draw from the implied posterior distribution of X underscore M. Then you can do, whatever it is you want with that posterior distribution. Okay, so we're out of time today. We will talk more about missing data on Thursday, in addition to going over the homework.